Another way of modeling a joint probability density function given marginals are copulars. And here's the setting. So assume a d-dimensional random vector. As always, it's called Z, and it consists of the d individual random variables. And again, I'm assuming that I'm given the marginal distributions, but nothing else. So we now follow a similar strategy. So the idea is similar to NATAF in the sense that I transform to a standard case. And in the standard case, I have ways of modeling this. As for NATAF, the only difference is now I don't use Gaussians, but I use uniform random variables. Yeah, so I leave more freedom in the sense that I do not prescribe the covariance. Yeah, so the idea is similar. So I'm setting now yi as fi of zi. So I insert my random variable into its CDF, which seems weird at first, but then you realize whenever I do this, independent of what this random variable is, out comes a standard uniform random variable, and the proof is the same as for NATAF. So I ask for the CDF of y or of yi. So that's the probability of yi less than or equal to the little yi. I insert what yi is, and then I operate inside the inequality with a monotone function. So fi inverse of yi, and now I know that the CDF of zi is actually fi. So I have fi of fi inverse of yi, and the inverse cancels. And if I look now at the CDF of a standard normal random variable, well, it has this PDF. So if this is y and here is f of y, the PDF looks like this. So here's 1, here's 1. It's 1 here. So its CDF actually looks like this. So it's f of y on the interval 0, 1. It's the identity, and then it continues as 1. And that's what I've computed here. Yeah, so it's the identity on the interval that matters. And now, well, the idea is now I have from these variables ci, I have a lot of uniformly distributed random variables. And we now look for a joint distribution on the unit cube, because all of my individual random variables are now uniformly distributed on 0, 1. So I put them together on the unit cube. And now, well, this is kind of the standard case. And this is what a copula actually is. It's an admissible d-dimensional joint CDF of uniform random variables. Yeah, so a function, it's called capital C for copula. It's a function from 0, 1 to the d into 0, 1 is a d-dimensional copula. If the C is the joint PDF of a d-dimensional random vector with, well, on the unit cube with uniform marginals. All right. And now in a second we're going to look at copulars, but if we have one, a copula, we're done with the construction. Then we have a joint CDF for my uniform random variables, and therefore by transforming back we have this. So the CDF of Z1 up to ZD is actually the copula, and I insert F1 of Z1 up to FD of CD. Yeah, so the transformation that I just prescribed to you, so these individual transformations transform to uniform 0, 1, and then I insert this into the copula, and that's my CDF. Well, and by construction, this preserves the marginals. So if we have a copula, then we're done with our original question. Now, what's left to do is to study copulas a little bit, at least. But you can read statistics books that are solely dedicated to copulas. But I just give you the short of it. So there's one theorem that's always cited when you do copulas. So the use of copulas is motivated by Sklar's theorem, which says that there always exists a copula. So that F be a d-dimensional CDF with marginals that are F1 up to FD, and then there exists a copula such that I can write the original distribution function in terms of the copula, such that well, the joint CDF is actually written like this. So in a certain sense, it's a completeness result that copulas give me all of the possible joint PDFs. So what's a little bit more important for the practical application is the following theorem. I can recognize from a function C when it is a copula. So let me write this down and then explain it a little bit. So a function C, 0, 1 to the D with values in 0, 1 is a copula. So if double F stands for if and only if, the following properties hold. So it's 3 properties by which I can recognize a copula. And the first one is this one. I insert 1 into all arguments except for the jth one. That's like evaluating all other random variables at 1, which means at the upper end of their domain of definition. And so I'm just integrating them out. It's like taking marginals, so I get only the uj. Yeah, so it's the marginal property of copulas. Then what we also kind of need is a generalization of monotonicity, so it's called isotonic. So if I have 2 vectors in Rd and the less than or equal means component-wise. So all the components of u are less than or equal to the corresponding component in V, and then we want that C of u is less than or equal to C of V. That also makes sense. It's the monotonicity property of cumulative distribution functions. And then finally, I want to explain the last component. It's called de-increasing. It's actually another way of expressing this monotonicity. So it says the following thing. So the value of every box which I write as an interval, but it means it's made up of a Cartesian product of individual intervals. And for this to be an integral interval, I need u less than or equal to v. So the value, and by value I mean as measured with c, is non-negative. And well, what does measured mean? Let me give you an example. In 2D, I can draw this for you. So I have a two-dimensional copula. And this one, the box, is, well, U1, V1 cross U2, V2. Then de-increasing means the following thing. Well, so let me draw a picture first. So here we have U1. No, not U1. We have U, and here on this axis we have V. So we assume we are on the unit cube. Yeah, so that's the unit square here. And then I have a U1 here and a U2, and then I have a V1 and a V2. And they are increasing, and they define a rectangle in the set like this. And now I would like to measure the rectangle by the measure that's given by the copula. And what do I actually need when, or what do I actually do in order to compute the measure? So assume we have a PDF of the measure, and let's maybe call this little c. Then I can write this value of the box, or the measure of the box, as this one. So I integrate from u1 to v1, and I integrate from u2 to v2, and I integrate the little c, uv dv du. And then I can assume now I have a corresponding CDF. Yeah, so first I would evaluate with the primitive with respect to v. So that's maybe a C with an upper index v at u and v, and I evaluate it at, and there's a mistake here, I'm integrating u1 up to u2 and v1 up to v2. So here I would evaluate this at v equals v1 up to v2 and integrate over u. So u1, u2, and that's also a u2 up here. Yeah, so I've made corrections here and in this integration. And well, here I would take this primitive that's only with respect to v and evaluate it at the upper bound minus v evaluated at the lower bound, and then still integrate over u. And this now finally is the primitive with respect to u, so that is my copula. So, and now I have the copula uv2 minus c of uv1 evaluated at u from u1 up to u2. And so I get that this is c of u2 v2 minus c of u2 v1, and then lower bound minus c of u1 v2 minus c of u1 v1. And that's precisely the property that I need. This whole thing in the end needs to be something non-negative because it's supposed to be a measure. Yeah, so I have, coming back to the picture, that I have this the copula evaluated at the top right point minus this point, and then a minus again, this point minus this point, or vice versa with the two axes changed. Yeah, and that's actually what de-increasing means. It means that I'm ultimately dealing with a non-negative measure here. And I'm not proving this theorem to you. It's not that simple, but you find it in books on statistics when you look into copulas. But I hope I can at least make these, or I could at least make these three conditions plausible for you.